Hello. Hello. Uh, Welcome to our section 12 on beliefs, conflict, and knowledge. My name is Reno Zhang from University of Hong Kong. So today we are very honored to have three speakers, Nicolo, Yongju, and Romila, okay, to give their presentations. So to start with, okay, we have Dr. Nicolo Meneghetti from HPE Vertica. So he will give his talk about better probabilistic databases, a scalable approach to belief updating and parameter learning. All right. So without further delay, okay, Nicola, please.
Hello? Okay, much better. So hello everyone, and thank you for being here. My name is Nicolo Meneghetti, and I will be presenting my work on probabilistic databases done in collaboration with Oliver Kennedy from SUNY Buffalo and with Wolfgang Gatterbauer from CMU. So this slide presents the general picture. We will see it many times during the presentation, and we'll understand the several parts of it in a progressive way. So for now, I will just give you an overview of what this talk is about. So the idea is that we start with a probabilistic relational database. For example, a relation storing information about people and their employees. And so since this is a probabilistic relation, we are not really sure whether the facts that are expressed in the relation are true or false. So we are not really sure whether ADA works for HP or not. And what we do receive in terms of information are sample query answers. So we had a set of oracles, and they can give us answers to Boolean queries of their choices. So we receive information like, for example, one oracle may say, I believe Ada and Bob work for the same company. Another oracle can come up and say, I believe that Ada doesn't work at all. So the feedback can be conflicting. So the goal of this topic is to show how we can integrate this sort of feedback into a probabilistic model over the relational data. So before going into the details, we need to introduce some background. So I'm sure many of you already attended the talk on provenance, so you're already familiar with it. So in this context, it is sufficient to say that given a conjunctive query, we can annotate its output tuples with Boolean expressions that represents the lineage. So how we got that result, that tuple in the result. For example, if we are querying this database and we want to know whether there is an employee that is English speaking at all, then what we would do is we would take a join of R and S, and then we would project away all the attributes except for the language. And so the result would have these two lineage formulas. So a little bit of background also about probabilistic databases. The model that we adopt is the most simplest one, so tuple independent probabilistic databases. So they look just like a regular database in which we annotate each tuple with a marginal probability. So the idea is that one tuple-independent probabilistic database can be in a number of possible words, one for each subset of its tuples. And we can also compute a probability for each possible word, which would be just the probability of selecting its tuples. For example, in here, for this simple relation, we have, let's say we have only 3 records, and we have a total of 8 possible words, so 2 to the power of 3. So in the first possible word, we have all the 3 tuples are present. In the second one, we have only the first one and the second one. In the last one, the database is empty. So beyond defining a probability space over the possible word, we have also probabilities over Boolean queries. And so the probability of a Boolean query would be just the sum of the probabilities of the possible words where that Boolean query returns true, or if you want, where the lineage of that query is satisfied. So if you are wondering whether DASA has a job, then we can just count the possible words where that happens, which are the first 6. So usually we don't really need to go through all the possible words. We can factorize the marginal probability in a polynomial way. And this happens whenever we can express the lineage formula as read once. So lineage formula is read once whenever each literal appears almost once. And for example, here we were lucky, right? Because does ADA as a job is definitely read once. So we start having a picture that is a little more clear. Now we know that the evidence comes in the form of Boolean queries annotated with their answer. And now we know that we can rewrite this in terms of Boolean expressions. So it's going to be just the lineage of the query or its negation, depending whether the answer was yes or no. And again, the goal is that we want to use this information to train a probabilistic model, so to refine our parameters. So let's see now the key idea at the base of our model. So what we propose to do is to generalize the tuple-independent probabilistic model by applying beta priors. So in the original model, we have that each tuple is annotated with a Bernoulli distribution, right, with parameter theta. What we have now is that each tuple is annotated with 2 values, so 2 parameters. And this happens because now we are associating each tuple with a beta Bernoulli compound distribution that is represented over here. So in the original model, theta was a parameter. Now it is a beta distributed latent variable. In both models, x represent a Boolean variable, so the event that the tuple is there in the database. So let's discuss a bit the properties of the beta Bernoulli compound distribution. So the first equation represents the probability density for the latent variable theta. So it is just the beta. And about the beta, we have to remember only a couple of things. So it belongs to the exponential family, and it is something that we will take advantage of later. And it is the conjugate prior of the Bernoulli. So the second equation shows the marginal probability. So how would you compute the probability, for example, that ADA works for HP in this model? So it turns out that the marginal probability equals the expected value of the latent variable theta. So this is an important result because it tells us that we can always convert a beta probabilistic database into a regular tuple-independent database. And so we can apply all the inference techniques that exist for the original model to our new model. And so every time we are only a linear transformation away from using whatever method we choose. Another important point is the posterior. So a big part of this presentation is going to be about computed posteriors. So for this particular compound distribution, we have that the posterior is in the same family of the prior. And this happens just because the beta is the conjugate prior of the Bernoulli. So the posterior represents our belief about the latent variable theta whenever we see a new sample for the Boolean variable latent x. So for example, whenever someone tells us, oh, I believe x is true, then our belief about theta is going to be the same as the prior we have in the beginning, except that we increase a by 1. If someone tells us x is actually false, then it is b, the parameter that we increase by 1. So let's see this in practice. Let's say we use this compound distribution to model a coin. In this case, the latent variable theta represents the bias of the coin, while x represents a sample of one coin toss. So let's say in the beginning we decide we want to make an unbiased assumption, so we don't know anything about the coin, and we set a and b to 1. This is the maximum entropy configuration of the beta distribution, and so you see that in this case it equals a uniform distribution. So at this point we know nothing about the coin. Then we observe the first throw, and someone tells us that it was head, so we have a little bit more information, and we increase parameter a by 1. Let's say that next time we observe tail, then it is b to be increased. Notice that the entropy is going down because we are getting more information, and so the distribution here is getting more peaked. And so we can proceed this way for multiple observations. And so every time we update our current estimate of the bias, which again is going to be just, the inner transformation is going to be just a divided a plus b. So now we start understanding a little more of how this model works. So we said now we have two parameters for each tuple. And now we start understanding what this means. For example, in here, we are saying that the state of the database is like we had asked 10 people about whether Ada works for HP, and 6 of them told us she does, and 4 of them told us she doesn't. We asked the same question about Ada and IBM to more people, and the fraction was the same, and the same for Bob. Now notice, for example, that the first two tuples have the same expected value for theta, though the distribution is different, so the entropy is different. We are way more confident about Ada being working in IBM with probability 0.6 that we are about knowing that Ada works for HP with probability 0.6. And also at this point, we know also how to make simple updates, right? Because if someone comes and says, hey, as far as I know, Bob works for HP, well, the update is going to be really easy. We are going just to increase the A parameter for Bob. And we can start also looking at queries. So let's say someone tells me that the select query should return false in his opinion. Then, so this is saying that in his opinion, no one works for HP that is in the database. And so what should we do is we should increase the B parameter for Ada and Bob by 1. Now, here the things to notice is that this update has a stronger effect on Bob than it does on Ada. And the reason is that we had more confidence, more information about Ada. And so this new sample has less effect. Now, the promise of the talk was that we were going to incorporate any arbitrary Boolean conjunctive query. And so what about if the feedback was no? In this case, we don't really get away just increasing one of the counters. And so the general idea is that we'll try to replicate what we did with the coin. So we will compute a posterior, we will update some priors so to match the posterior, and we'll keep repeating that for each and every sample. Sorry. So we need to introduce some new concepts. So first we introduced the concept of conditional probabilities that was started in the beginning in a paper from Koch and Olteanu. So conditional probability just represent the probability that a query is true given that we know that another query is satisfied. For example, we could say that phi prime represents the lineage of the query. Ada does have a job, while phi represents the lineage of a query saying Ada works for HP. Then this probability is just saying, okay, what is the probability that Ada is working in HP, given that we know she's working somewhere? And the second one is the big one, which is the posterior, which is what we need to make our belief update. So the posterior represents our belief about the vector theta, so the vector of all the theta variables in our database. Once someone comes and tells us, gives us an additional sample regarding phi. For example, someone tells us that as far as they are concerned, Ada does have a job, without specifying which one. So, okay, now we move the posterior up here, but now we introduce another thing, the marginal posterior. So since our model is tuple independent, we want to throw away and consider as noise all the correlations between the components of the posterior. So what we do is we compute a marginal posterior. So we marginalize away all the components except one, and we do this for each and every latent variable that we want to update. So now computing this would be really expensive if we were doing it brute force, just following this expression. So one of the main results of the paper is that indeed there is a much better way to compute that measure. And so we proved that indeed the marginal posterior consists just of the mixture of two beta distributions. So notice the coefficients are just the conditional probability of the evidence of the literal that we want to update given the evidence. And notice also that those two values sum up to 1, so this is a mixture. And the component of the mixture are just the update that we would do if we were observing either the literal itself, so Ada works for HP, or its negation, so Ada works somewhere else. So we are almost ready to do our Bayesian update, but not quite. And the problem is that we are not anymore in the context of conjugate priors, because a mixture is not a beta distribution. So in order to adapt the prior to the posterior, what we do is we minimize the relative entropies between the two. And it turns out that now we can exploit the property of the exponential family. So in order to minimize the KL divergence between the marginal posterior and our prior, we just need to set the prior so that this set of constraints is satisfied. Notice that this has constant complexity, because for each tuple we have exactly 2 constraints and 2 variables. So we explained how you would integrate a single observation. Now I will go quickly over how you would that for multiple observation. And the general idea is that you would replicate the model. So you would use k distinct replica, one for each distinct lineage formula over which you have feedback. And S in this case would represent the number of samples. So in total, we would have k times S replication. And the goal, I will not show the details, but the final result is that we can collapse multiple observations in a single belief update step. So this means that instead of just doing this, we can also integrate feedback like this, so noisy feedback. So someone can say, I believe Ada works for HP with probability 0.7. And still, we are able to make a Bayesian update. So many of you probably already noticed that this belief updating procedure is one of the many incarnations of expectation maximization. In here, expectation would be a computation of the conditional probabilities, while the maximization step is the optimization problem that I just presented. And so here we have an example. Like all algorithms in the EAM family, we can use it for maximum likelihood estimation. So in here, the oracle is saying just 2 constraints. It's saying that we have only 2 tuples, and the probability of observing both should be 0.32. The probability of observing at least one of them should be 0.88. And in the plot, the surface represents the likelihood, so the probability that our current model will generate the evidence, so we'll satisfy the constraint. And we see, so each dot here represents a belief update. So after about 100 updates, we reach one of the maxima of the likelihood. So complexity results, I really need to go really quick about this. So I will just say that there is a very large class of queries that is known to be tractable for probabilistic inference. And in the paper, we proved that indeed we can do Bayesian updates on those queries in polynomial time. So we can collapse as many queries as we want, and still the complexity is going to be polynomial in the query size. So brief recap. So we introduced a new model for probabilistic databases. The main idea is that we impose priors. We show that we don't pay any price for moving to this model. We can use all methods for inference. We show that we are able to integrate information in the form of query answers, and they can be of any form. And if they are hierarchical queries, we can do everything in polynomial time. And also, we show that if we do multiple Bayesian updates, we will finally converge to a maximum likelihood estimator. So we are able to build unbiased estimators. So benchmarks, I will explain this really quickly. There is a similar paper by Dilla and Theobald. And the problem they address is someone comes and gives you a set of queries and target probabilities, and you want to train a model so that it will respect all the constraint. And the solution is to apply a gradient descent approach. And so in the benchmark, what we were comparing is our expectation maximization technique, which is in red, against several variants of gradient descent. So we have regular gradient descent and 2 variants of stochastic gradient descent. So thank you so much for the attention, and of course, if you have any questions.
Any questions? Thank you for the interesting talk. I just have a quick question. So in your input data, do you assume that all the input from the user is either yes or no to some of the questions? So can you give more information about your experiment setup, about what kinds of questions you issued, and what are the formats of the answers?
So yes, the evidence shows up always in the form of independent samples to Boolean queries. So whenever someone says yes or no, it is always independent from his previous answers and from the answers of the other judges. So the only possible change here is that we may have noisy evidence. So we may have someone says, I believe this is true, but with probability 0.9. So I'm not really quite sure. And so that's the only variation. For future work, we definitely want to study how this world model could be generalized for handling answers that are not Booleans. For example, I believe the age of Ada should be around 35. So if I say that, then I am defining a probability distribution over the possible values of the age of Ada. And so that would be a definite model.
Okay. Thank you very much. Yes?
A slight variation of a previous question. So sometimes it's not just you don't get a yes answer because it's just missing or it's just uncertain. I mean, because you cannot just get either yes or no. Sometimes you just don't know. I mean, for majority case, you have a large time missing data. So how do you kind of handle that part?
So the oracle is allowed to return noisy readings. So for example, if the oracle says, okay, query 1 should be true with probability 0.5, it is the same as saying I have no clue about this query. And so we can integrate that kind of information. So one of the possible ways of integrating feedback is indeed integrating this sort of statements. So for example, I believe that that works for HP, but I am not really quite sure. So I will say, as far as I'm concerned, the probability should be 0.9, for example.
Okay. Any other questions? Okay. So if not, let's thank the speaker again.
Thank you.
Next, we will have Dr. Yongju Park from University of Michigan, Ann Arbor. So Yongju will be talking about database learning towards a database that becomes smarter every time.
Okay. Good. Let me change the, let me pull on my slides, which is not here. Okay. My name is Yongju Park, and I'm going to present database learning. This was joint work with another student, Shahab Tajik, and my co-advisors, Mike Afrella and Barja Mujaffari at the University of Michigan. So let me get started. Today's database workflow is like this. User submits a query, and they compute the answer, and they return the answer. And after returning the answer, they just discard the answer. This means that they are also discarding the work performed to compute those answers as well. The work includes CPU computations or I/O communications, and so on. So the goal of this talk will be we want to use those answers for speeding up the query processing speed. So in this talk, we apply this idea for the approximate query processing, or simply AQP. The workflow of AQP is basically the same. User issues a query, and it returns the answer. Same. Only difference is that the answer is approximate answer, and if you allow more time for the database, then it can return more accurate answers. That's the only difference. So our contribution in this talk is this middleware between the users and the AQP system. And from now on, I'm going to call this AQP engine just underlying AQP engine because it's underlying. And this our system, database learning, has its own data structure, which we call query synopsis. And query synopsis is basically containing the past queries and the answers to those past queries. And we're going to exploit this information in the future. So users submit a query now to this database learning system, and we simply force the query to the underlying AQP engine. And it returns the answer, approximate answer. And we somehow improve the quality of this answer when we return the answer to the user. I'm going to explain about how we actually do that in the following slides. But we are doing that by using some information coming from the query synopsis. So why is this good? So let me take a look at the relationship between the runtime and the error of the approximate query processing. So if you simply use a AQP engine, then it looks like this. If you allow more time, then the error decreases, right? Very straightforward. If you use our system, then the relationship between the error and the time looks like this. So this has two types of benefits. The first benefit is that if you're interested in a certain time-bound query, then we actually provide error reductions, right? And if you're interested in certain error-bound query, then we can process the query faster, which means we provide speedups. So they are the two types of benefits. So applying this idea, exploring the answers to the past queries for improving the quality of new answer is not easy because different queries might touch different combination of rows and tuples, like this. So the core technical question is, how can you actually achieve this goal? So our idea is this. So we assume that there exists some underlying data distribution that generates your table. We don't know what the distribution looks like. But we're going to do something interesting based on this assumption. So user submits a query. It might touch some combination of rows and columns, and we compute the aggregation. And based on this information, we update our knowledge about this underlying data distribution. And there is another query that touches different combination of rows and columns. And based on this another pair of query and its answer, we refine our knowledge about this underlying data distribution again, like this. And as we observe more queries and more answers to those queries, we keep refining this process about our knowledge about the underlying data distribution, and we are going to use this information for updating the quality of the new answers. So how it actually looks like, let me give you a more concrete example. So this is a true data. I'm visualizing the word count over time, and this is true data. And let's say that these are the gray areas are the past queries we processed. And based on this information, our system actually builds a probabilistic model that looks like this. So since our model is a probabilistic model, you can see that we are also visualizing 95% confidence intervals using the shade area. And you can also observe that around these gray areas, the confidence interval is actually narrower, indicating that we have more accurate knowledge about around those areas because we made observation. So as we process more queries, we keep refining our knowledge. So you can see that actually model is getting more accurate and accurate towards the true distribution. So when we apply this idea for the actual query processing, we had 3 design goals. The first goal was we wanted to support a wide class of SQL queries to be practical. And the second goal was we didn't want to make any assumptions about the underlying data distribution. So in other words, we are not making assumptions like underlying data follows some linear or quadratic function like that. We don't assume that. And third, we wanted to make this estimation or the inference process for improving the quality of a new query as fast as possible so that we can provide enough speedups. So let's take a look how we actually achieve this. The formal problem statement looks like this. Given past queries, a new query, and the approximate answers to those queries, we'd like to find the most likely answer to this new query and its estimated error. And our result is this. So under certain assumption, our error bound or our expected error is not larger than the original answer's error. But basically, this means our answer is better. So let me give you a high-level overview of our technique then. So let's say there are 2 past queries and 1 new query. And you can see that in this case, this is a simple case, the answers to these queries are scalar values. I'm going to handle more complex cases in the following slides. In this case, we model these answers to these possible answers to these queries using some random variables. In this case, because there are 3, we are defining 3 random variables. And then, this is an important step. We determine a joint probability distribution function to describe the relation between those random variables. And this joint PDF sounds like very complicated, but the intuition behind this joint PDF is really straightforward. This basically tells that if 2 aggregations include some common or correlated tuples for their aggregations, then their results of their aggregations should be correlated as well, right? That's very straightforward. So this joint PDF is just a formal way of expressing that idea. And then given this joint PDF, estimating the most likely answer to the new query is pretty straightforward. It's just a conditioning process given the answers to the past queries. So I'm going to describe each step in more detail. So how do we define the random variables? So we define a random variable for every combination of this aggregate function and the selection predicate. What if your query is more complex? Then we can decompose this complex query into these multiple simple queries. And then we can get we can estimate answers to these simple queries, and then repopulate the answers to this complex query. So in the rest of the talk, I'm going to focus on answering these simple queries. And the second step, if you remember, was determining the joint PDF for those random variables. So for determining the joint PDF, we used a statistical principle called the principle of maximum entropy. So what this principle does is basically, given some amount of statistical information about those random variables, it just gives us a most likely joint PDF, given that information. So when we use this principle, there are some considerations. If we provide low amount of information to this principle, then it basically returns a simple joint PDF. The advantage of using simple PDF is that the inference speed will be fast, but the downside is that the quality of a new answer will be low. If we provide more information, then we get more complicated joint PDF. In that case, the speed of inference will be slower, but the quality of the new answers will be low. Quality of the new answers will be good. So we need to find a good balancing point between these 2 points. So the types of statistical information we provide to this principal in this talk is the covariances between those random variables. So if we provide the covariance information to this principal, then basically the principle of maximum entropy tells us that the most likely result in PDF is the multivariate normal distribution. And this result is really nice because multivariate normal distribution has been extensively studied in the literature. So for the conditioning or the inference process, we can simply use a closed form solution for estimating the most likely answer to the new query, given the observation, given the answers to the past queries. So that's really nice. So compared to other techniques, for example, compared to indexing, our benefit is that because we are only storing the answers to the past queries, not the raw tuples used for computing those answers, our storage cost does not grow even when the database size grows. And compared to materialized view, our technique is much more general because we build a model and use that model. So we can provide benefits even when the new query is not aligned with any of the past queries. Materialized view cannot handle this. And due to the nature of our processing or our approach, we do not have any upfront costs. We just gradually learn or improves. So these are the experimental results. Let me present the experimental result. In the following slides, I'm going to compare two systems. First system is the no-learn system, something we call no-learn. It's basically a proximate query processing engine. And if we allow more time for this system, it's going to return more accurate answers. And our system is something we call verdict. Is implemented on top of a no-learn system. This is our database learning system. And for the data sets, we used the two data sets. First was actual customer data set, and the second was the benchmark data set. And we ran the experiments on an Amazon cluster, and we stored the data either in SSD or in memory. So I'm going to make three experimental claims in the following slides. First is that we could support a large proportion of the real-world queries. And second claim is that we could provide enough significant speedups compared to no-learn system. And third, I'm going to show that our overhead was actually very low. So this is showing the proportion of the queries we could support in the customer dataset and the benchmark dataset. So basically, the types of the SQL queries we support are the flag queries, including joins with the dimension tables. So what we cannot support are the nested queries that cannot be flattened, because we basically support the flag queries. And currently we cannot also support the queries including texture filters. The reason is because I mentioned that in order to compute the correlations, we need to compute some expected similarities between the two queries. However, when the queries include the texture filters, that process is very complicated. However, if you can somehow figure out a heuristic method for computing the similarities even when there is a texture filters in the queries, then we can easily extend our current approach to support those queries. So let's take a look at the relationship between the error bound and the runtime. So this is basically the no-learn system. Looks very similar to the earlier example. So as we allow more time for the query processing, then the error gradually decreases. And when we tested our system, it looks like this. Because we are using some external information coming from the query synopsis that contains the past query and their answers, we are providing much lower error bound compared to the no-learn system. So let's take a look at the speed up in more detail then. So this first case is when the data was in memory. So from this graph, we can observe the two things. The first thing is that when you want a very accurate answer, our speed up is actually lower. This is because if we want exact answers, then we need to actually process all the queries for the new answers. So in that case, the approximate answers to the past queries could not help our system that much. And the second observation is that when the data was in memory, we could not provide a huge speedups compared to the underlying AQP system. And the basic reason is that the time we are minimizing is basically the data loading time and the computation time, not the a default overhead of the system. So if the default overhead of the system is a dominant part of your query processing, then actually in that case, we cannot actually provide huge speedups. However, when the data was in SSE, in that case, like in query processing, like a data loading becomes like a dominant part of your query processing. In that case, because we are reducing the data loading part a lot and the like, aggregation part by using the information coming from the past query answers, we could actually provide much more speedups in this case. So implication is that if the existing database systems like a default overhead actually decrease, like for example, like a Spark SQL's default overhead decrease, then in that case we can provide much more speedups actually. So let me show you the memory overhead of our system. So our memory overhead was very small because we are only storing the answers to the past queries. This includes some like matrices we had to compute for using the multivariate normal distribution. But even including that, our memory overhead was very small. And when it comes to computation overhead, I mentioned that because we are using the multivariate normal distribution, we can compute the inference process using a closed form. So that's the reason why this overhead was very small compared to the other query processing time. So that's all.
I think your approach essentially you are accumulating some data for each query, but I'm curious when I running your system for a longer time, I mean, how do you capture your kind of the total kind of data size because you keep accumulating those data sets. Essentially, you are building another database on the query result. So how?
Right. So the query result itself is very small, though, compared to the raw data used for computing the aggregations. So even when you're storing like thousands of queries, the total size of the query synopsis is just less than 100 megabytes.
Talking about at a 1,000 level, I'm saying that I'm running your system for let's say for 1 year, and then there are probably
in that case,
100 query per.
Yeah, that is a very good question.
Hour.
So I didn't mention a lot about how to manage those past queries. And currently we are using a FIFO style of query management. So we are just abandoning the old queries. But in the future, we need to figure out a better way to maximize the expected accuracy for the future queries. That's currently the future work done. I'm sorry. Oh, predicates? So I mentioned that for each predicate, we define a random variable, right? And for different predicates, we can compute the similarities of the query answers based on those predicates. So that's the basic idea. So if the two queries include very similar predicates, then their correlation will be very high, right? And their queries include very disjoint predicates, for example, then their correlation will be low. So we are basically exporting that correlation information between the query answers based on the predicates.
So it doesn't have to be linear, right? For example, if it's x greater than 10 versus x greater than 11, and the rows that have x equals
it's not linear. It's not
11
linear.
substantially change your answer, then how do you use correlation between these two predicates to?
So you're saying that when new query includes some predicates that we have never seen, and that query includes substantially different data values that can change the answer, query answer a lot, right? Is that your question? So okay, there is two parts. The first part is that even in that case, by accumulating the observations, we can still learn some underlying data distribution and make use of that. And I think you're more worried about accuracy of that answer, right? So in that case, we have another mechanism we actually described in the paper. I didn't tell you much about that. We have a safety mechanism to ensure that your answer is not doesn't deviate much from the true answer. We have another mechanism for that.
Our final talk in this section will be presented by Ms. Romila Prahan, okay, from Purdue University. So she will talk about the staging user feedback toward rapid conflict resolution in data fusion. Thank you.
Oh.
All right. So hi, I'm Romila Pradhan, and I'm here to present this work, staging user feedback toward rapid conflict resolution in data fusion. This is a joint work with Dr. Sergey Baiku when he was at Purdue University, and my advisor, Professor Sunil Prabhakar. So data conflicts are a reality in today's world. With the advent of Web 2.0, anyone can provide information about anything. And really, there is no restraint on the quality of information that one can provide. If you look at an example, you see in the top row there are sources, and in the leftmost column there are certain animation movies. So this data represents the information provided by the sources for directors of certain animation movies. A cell in this data is the claim made by a source towards any particular data item. So as you can see, for each data item there are multiple conflicting claims. All right. So the reason is that sources often make mistakes, or they copy from each other, or they plain and simple are lazy in updating to the most recent values. So whatever be the reason, we do not know which of these are correct claims and which are incorrect claims, right? So recently, a number of data fusion systems have been proposed that automatically distinguish true claims from false claims. We will look at such an example. So one such data fusion system we'll look at. This forms the basis for a number of other variants of fusion and is very easy to interpret. It uses some Bayesian analysis. So the model, it basically considers the claim provided by sources to be a vote of that source towards that claim, and it considers sources to be mostly good. Further, it assumes that for each data item there is only a single correct claim, which is one among those provided by the sources. So it characterizes the sources by their source accuracies. That is the probability that the claim provided by a source is correct, and further it computes the correctness of claims based on the accuracy of sources that provide that particular claim. So we see that there is an interdependence between these two parameters. So the model initiates with an initial estimate of source accuracies, and it iterates between these two steps until a stable allocation is reached, at which point it gives the output, and using the claim that a single claim is correct, it picks for each data item the claim with the highest probability of being correct and says that this is the most plausible claim for that particular data item. So far this is good, and this is how a majority, actually all of the data fusion systems have been working. They look at automatically distinguishing true claims and false claims by doing some internal computations. But if we look at, if we do a quick comparison with ground truth, we'll find that we are not doing good. So there's still room for improvement. What we are proposing in this work is that we go beyond what just the sources are saying. So this whole computation is based only on sources and just the data. So we propose that we involve a user. So we say that if we have a user and we can ask them that, okay, can you please tell us the correct claim for a particular data item, and if they provide us that feedback, we integrate that into our fusion model. So our objective is to improve the quality of the output of fusion, of the existing fusion models. So far so good, but users are expensive and we have a large number of claims to validate. So we want to be most effective with the user. So the key question that we answer is how to be the most effective in utilizing users' feedback. We want to prioritize certain data items that we should validate from the user before we move on to certain other data items. So in this talk, we'll talk about 4 ranking strategies. So we will look at all our data items and we'll rank them in a certain order and keep them validating in that order. So we look at 4 methods. 2 of them are item level ranking strategies. So they look only at single data items. and 2 are holistic ranking strategies. So they look at the global picture of global impact of all data items. Further, we touch upon feedback errors. We cannot assume the user to be an expert all the time. And we end with a discussion on our results. All right? So quickly moving on to our item level ranking strategies. The first one in this is query by committee, which is based on the simple intuition that there is a level of agreement and disagreement between the different sources for each data item. So for example, if you look at the data item Zootopia, there are 3 claims made by 3 sources, and there are 2 distinct claims, right? And we see that most of the sources, they agree on a claim. On the other hand, if we look at Rio, we see that there are only 2 claims given by 2 different sources, and the sources mostly disagree. So we assume that, so this method, it is based on this intuition that we probably are more certain about Zootopia because sources agree. We probably are not sure about Rio because sources disagree. So we will go and validate Rio first before we do Zootopia. That's all that we're doing. In this method, we're not using the output of fusion at all. But we say that while we want to improve the output of fusion, we would much rather do a better job by using the output, right? So we look at our next method, which is uncertainty sampling. This method looks at the correctness of claims, that is the output of fusion, right? So for each data item, you see what is the probability that a particular claim is correct. So in the top row, Zootopia has the probability of Harvard being correct with 0% of probability, and Spencer is correct with 100% probability. So this method is based on the assumption that the fusion model is mostly correct. So we tend to trust the model. So we say that if you look at Kung Fu Panda, it says that Nelson is correct with a high probability, 98.5%. And Minions is correct with, for Minions, Coffin is correct with a probability of 92.1%, right? So we say that probably the fusion model is more certain about Kung Fu Panda than it is for Minions. So we would go and validate that. So these are our 2 item level ranking strategies, and they are easy to implement, they are easy to interpret, and they are computationally inexpensive. So for if you look at QBC, we just look at the data for each data item, the claims for each data item, the distribution, and we compute the entropy for each data item, and we just sort in decreasing orders, and we do that once only, and that's all we do. For uncertainty sampling, we look at the output of fusion, we compute, we look at which item is more beneficial, and for each time we want to validate a data item, we look at the output of fusion once, that's all. However, what we observe is that for each validation, there are certain implications. For example, if we look at our data as it is, and if we were to validate Zootopia, that would change our belief in the correctness of claims Howard and Spencer. That in turn would change our belief in the accuracy of sources S2, S3, and S4, and that would change our belief in the correctness of claims of all these other data items. On the other hand, if we were to validate Finding Dory, that has just 1 claim, it would reach only 1 more claim, right? So we see that there is a implication of a single validation. We want to be able to capture that implication, and we want to be able to be as beneficial as we can. To do that, we use certain tools, the first one of which is an ideal utility function. We say that, okay, how do we know how good we are doing? For that purpose, we define the utility function to be it sort of measures the effectiveness of our fusion model. We say that if we had access to a ground truth function that gives us true and false labels for each of the data items, we compute the average correctness of all true claims, and that is based on the output of fusion, right? So this is our ideal utility function, which would work fine, but for this truth function, right? So this is not feasible. In order to do that, we propose a practically feasible utility function that does not use ground truth at all, that uses the output of fusion, and we call it the entropy utility function. It looks at the correctness of all data, the entropies of all data items over the correctness of all its claims. So in case of our ideal utility function, the closer that is to 1, the better the fusion model is. In case of this entropy utility function, the EU function, the closer this function is to 0, the better it is for our fusion model. So we want to be as close to 0 as possible. The second tool that we use is a borrowed concept from decision theory called as value of perfect information. What that does is, for computing the benefit of each validation, we look at what is the benefit, how do we improve the utility function for each data item, right? So we define it as the gain in the entropy utility if a particular claim is true. And we do this for each claim of each data item. So you see, in this formula in the EU on the right hand side, we compute the entropy utility function for each claim of each data item. So this is the best we can do in the absence of ground truth. We do not use ground truth, we only use the correctness of claims as output by the fusion model, and that's all. However, we found that for certain kinds of fusion models, for example, the one that we used that we adopted in this paper, which is an iterative fusion algorithm, MEU becomes expensive because we need to run entropy utility for each particular claim of each data item. We want to remove this bottleneck, and for that we propose a fourth method, which is approximate MEU. This is based on the key idea of propagation of changes. So if we validate one data item, how does that propagate to other data items? So we look at the correctness of claims of validated data item, how that changes. For this purpose, we look at we use something called as the approximation by differential methods, and we look at how the claims of the the validated data item has changed, how that changes the accuracy of sources that provided information for that data item, and how that changes the correctness of claims of other unvalidated data items. This method does not require us to fuse for every claim. So this removes the bottleneck for bottleneck iterative computation for MEU. And we show that this is scalable for large data sets, and we are able to do it for iterative fusion algorithms as well. That's all our methods. And so far we have assumed that we have access to perfect feedback. However, users can be wrong, right? So in this paper, we have also looked at 3 kinds of errors that the users can have. The first, when we have an honest but unsure user, we say that, okay, we are 80% sure that this particular claim is correct for a data item. We look at another error, which is the error rate of user. If we know that this user is correct 70% of the time or 80% of the time, we are able to incorporate this into our model and use that as the feedback. The third is when we crowdsource our feedback from a crowd of workers and we get conflicting feedback. How do we use that? Say we have 10 workers and we get conflicting feedback for 3 claims. One set of workers, they say that claim 1 is correct, 3 people say that claim 2 is correct, and the third person, the 10th guy, says that claim 3 is correct. So this integrating erroneous input into a feedback model, this required some work, and we had looked into the issue, and we are able to incorporate each of these user errors into a model in the form of certain probabilities of correctness of claims. More about this is in the paper if you would like to discuss more. And so quickly moving over to our results, we have used 3 data sets: the books data set, flights, and population. This has been the standard for most of the data fusion algorithms. And it's worth mentioning here that the books and population data sets, they are long tail data. What that means is that in these data sets, there are very few sources that give claims for a large number of data items, and most of the sources, they give claims for very few data items. So we have a distribution of conflicts in claims. Further, for the user feedback framework, we simulated feedback in the form of ground truth that we obtained from the authors of the different papers. So a quick information about the different feedback simulation is here. Our competing methods, we look at how well we are doing in terms of our methods with respect to the greedy upper bound, which is the ground truth utility based method, and we compare that to the baseline, that's the random method, that looks at all data items being equally beneficial, and it picks any single data item of validation randomly. So we expect to see a graph between the random baseline and the greedy upper bound. So what we want to see now is that in the vertical axis, how does the distance to ground truth, it keeps on decreasing as we validate more data items. So we see that initially we are at a very large distance to ground truth, and that keeps on decreasing as we validate more data items. What we found for our long tail data is that when we have large number of sources and very few claims, our holistic ranking approaches, which is MEU and approx MEU, they almost always outperform the item level ranking strategies, right? This is because for the long tail data, we do not have a very nice distribution of claims. So for each data item, we have only 2 or 3 different claims. So we do not, so QVC fails there. Uncertainty sampling also does not perform well because we get very, very polar correctness of claims. So we're not able to differentiate between the different data items on the basis of US uncertainty sampling. However, holistic ranking approaches, they almost always perform much better than the item level ranking strategies. The same is for our large scale long tail data, and as you can see here, we were able to run MEU because for each data item we had very few claims, so we were able to go full-fledged to the MEU method. And as you can see, approx MEU is as close to MEU as is possible, and this data set had very few data items that had conflicting claims. So once those were validated, all the methods were actually the same after the first 120 were validated. On the dense data, this was interesting because on the dense data, when we have very few sources providing claims for very large number of data items, both of our methods work well. So either QBC or the holistic ranking approaches, both of them work well. Uncertainty sampling also, as you can see, it decreases the distance to ground truth as we validate more data item, but it does not perform as well as QBC and approx MEU. This is because in such data set, because of the excess of information that we have, the correctness of claims has a high polarity again. So uncertainty sampling does not perform as well as QBC and approx MEU, but yes, surprisingly, one of our item level ranking strategies, which is QBC, it performs comparable to approx MEU and MEU. The same is for our large scale dense data, the flights data set. We were not able to perform approx MEU throughout because in this data, what happens is that when you validate one data item, that changes some correctness of claims across all the other data items. So this was very expensive, and so we were able to look at some workarounds where we, instead of looking at all data items, we look at a small sample of a subset of data items, and we look at what is the impact of a validation on this subset. So that is a black line, and we see that even with a very small number of data items, like 10% of all data items, we are able to, so approx MEU still performs better than QBC, but I should mention that QBC is more efficient and probably is a better choice than approx MEU in such cases. So that's all. What we showed in this work is that by integrating user feedback into the data fusion models, we can improve the performance of existing fusion models. So our framework is easily pluggable to any data fusion model, be it iterative or non-iterative. We design strategies to generate effective orderings of in which data items should be validated, and we were able to provide scalable decision theoretic solution for iterative fusion algorithms, and we also explored some feedback scenarios. And our evaluation on the 3 real-world data sets showed that guided feedback will rapidly improve the effectiveness or the performance of data fusion models almost all the time. So that's all, and I'll be happy to take questions.
So thank you for the nice talk. I just want to have a quick question of asking about whether you have also considered the literature in crowdsourcing in how to do truth inference. And
What?
truth inference. Basically, you collect data from different workers, and then you have to consider the quality and the performance of the workers in deriving the true answers.
Yeah, so we have not looked, so we understand that crowdsourcing is slightly orthogonal to our work. So we have not looked at modeling a user's behavior. But so what we have assumed that if we have a crowdsourcing system that is able to give us a single most correct label or conflicting feedback like 3 out of 10 are saying one is correct, 5 out of 10 are saying a different is correct, we are able to input that into our system. So, but we have not looked at how to make the crowdsourcing system work. So that is slightly orthogonal. So this is a feedback framework that we are using. So and we say that the crowd is giving us feedback.
Yeah, because I can see that the framework of the feedback is actually very similar to the crowdsourcing platforms, and maybe you can consider using platforms to collect more data for experiments.
Yeah, we have looked at only one. Actually, if you look at 2 of our errors, so the error rate of user, in that also we are assuming that if we have a single correct label from a crowd, and we know that the crowd, we know that how often the crowd is correct and how often it is wrong. We are able to incorporate that into our feedback framework. And the second is that if we know such a distribution that the crowd is having a conflicting consensus about different claims, we are able. That's the third bullet. We are able to incorporate that also into our framework.
Yes.
So that's all.
Yep.
Okay.
Any other questions? All right. So if not, let's thanks Wamila again. Hey, thank you very much. So that's the end of this section.
Thank you so much. Did you have this one? Yeah. All right. Hi. Was it fine?
Yeah.
Okay.
There you go.